All right, so we're continuing here with our discussion about electrophilic aromatic substitution reactions. And we were talking last time about how when you have benzene or benzene derivatives, which would occur when you substitute something onto a benzene ring, they undergo EAS reactions, right? That involves the pi electrons from the benzene ring attacking some strong electrophile. It has to be pretty strong because the resonance and aromaticity of this ring makes it relatively stable and low in energy, so you need a relatively high energy electrophile to attract those electrons out of there. So today we're going to look at what happens when there's something else on the ring other than the ring being bonded to 6 hydrogens at each of these positions all the way around. If there's a methyl group or an oxygen or a nitrogen or a CO2 bond or something like that, Nitro, lots of different groups could be connected to the aromatic ring. We want to see how they affect the likelihood that the aromatic ring will pick up an electrophile and the regiochemical outcome of those reactions. So one thing we can take a look at here is the kinetics, which tells us about the rate of the reaction. And so if we were to compare toluene undergoing nitration versus benzene undergoing nitration, so that would be this reaction here with benzene, I would use HNO3, H2SO4. That reaction we talked about last time before spring break would put a nitro group on there. If I start with toluene rather than benzene, toluene has a methyl group. At this point, all 6 carbons are equivalent, so it doesn't matter where I put the methyl. But once I put the methyl group there, I still have a plane of symmetry here. So this position and this position, I'll call those A, those are equivalent. B is equivalent to B, and C is here, but those are going to be different regiochemical outcomes compared, depending on where the nitro group ends up relative to where the methyl group's located. I might get a few different products, right? So that's what we're looking at here. And we want to consider what the product is, but also how often the product will be produced or the rate at which it's produced versus the nitration of benzene. And so we see here that toluene causes the reaction to be 25 times faster. So that tells me that the collisions that occur between the benzene and the NO2 electrophile, right, the nitric acid and sulfuric acid produce NO2 as an electrophile, and the benzene electrons will attack there. During the attack, during the transition state of that attack, if the attack occurs with toluene instead, it occurs 25 times faster or more often. So that tells me that the transition state energy is lowered by the presence of this methyl group. Or in other words, the methyl group activates the ring. What we mean there is that it lowers the transition state energy. And so we want to be able to explain how that works. And at the same time, we're going to look at whether or not the nitro group's more likely to connect at position A, B, or C, because those two things are related. So that's what we're going to talk about next. Try to explain why the methyl group affects the transition state energy for the aromatic pi electrons attacking the nitro group. So here are the 3 potential regiochemical results. When 2 groups are positioned on adjacent carbons on a ring, that's called ortho. When they are positioned 3 carbons away from one another, that's called meta. If they're positioned 4 carbons away, that's called para. And when we look at the distribution of products, ortho, meta, and para products, where the nitro group gets positioned in one of those 3 spots, we find that the meta product is a very minor product. Almost none of that forms. The reason for that is the same reason why the reaction is faster with the methyl group versus if there were a hydrogen here. And that has to do with the transition state, right? So we can imagine when the pi electrons attack the NO2 group to attach the nitro group to the ring, the pi electrons could reach out and do that from the ortho position or from the meta position, or it could be the pi electrons that attack from the para position. If the transition state energy is not the same for each one of those attacks, then they won't all occur as often. And that's what we see, different rates of the different reaction occurring. We do have to also keep in mind, though, that this ortho product is the same as this ortho product. It just rotated or flipped over like a pancake. These are the same thing. So statistically, if there were no difference in the transition state, if the attack from the ortho, meta, and para positions all went through the same energy for their transition states, they would occur all equally as often. But statistically, since there are 2 possible positions on the ring, that would result in ortho products, and 2 possible positions of attack or connection on the ring that would result in meta products, and only 1 position on the ring, the attack would have to occur in this specific position to produce a meta product. I would normally expect to see twice as much ortho and meta as there is para, statistically. Or 2/5 of the product would be ortho, 2/5 would be meta, and 1/5 would be para. But that's not what we see. So we have to recognize that the resulting products depend not only on where the collision could just more likely occur based on statistical random probability of which carbons the NO2 collides with, but also it depends on the transition state energy associated with how stable it is during that collision. And so that's what we also want to look at. So the textbook focuses more on the intermediate that's formed rather than the transition state. But we know from kinetics, it's the transition state really that's the most important part. So let's draw the transition state for this collision at the ortho position. So what would happen here would be that this pi bond would start to break, and it would start to form a new bond with the nitrogen. And one of these pi electron pairs from the nitrogen to the oxygen would break and move out to the oxygen. So the nitrogen would still be positively charged. It has new electrons coming in as old electrons leave. This oxygen up here is starting to pull more electrons, so it would start to become negative. This carbon right here had some electrons there, and they're just going to move over here. So it really has the same number of electrons around it. If a carbon has 4 bonds, which it does because there's also hydrogen there, and as one of its bonds breaks, another forms, it's not really gaining or losing bonds. So its partial charge is still 0. It has basically 0 charge there during the transition state. But this carbon here, as the electrons get pulled away from it, it starts to take on a partial positive. And that can immediately be stabilized through resonance. So this pair of electrons can start to shift over there, not entirely, but it can start to and pull electrons away from that side, and these can start to shift over and pull electrons away from that side. So during this transition state, I'm starting to form a carbocation that you can see here in the intermediate, and it's starting to form on the same carbons where the carbocation would form in the intermediate. And since one of those is tertiary, in addition to the others that are secondary, that's somewhat stabilized. If we did the same exact transition state starting from benzene without the methyl group, so we're working with benzene instead of toluene, it would look very similar. Except in this case, all of the sites that help to stabilize the partial positive are all secondary. So if we call this A and this B, and we were to look at the reaction coordinate diagram for this reaction, just looking at this key slow step of the process where the aromatic ring attacks the electrophile, for A, since the transition state has all of the partial charges forming on secondary carbons, it's relatively unstable. And so is the intermediate that forms. And so that would be if benzene were the reactant attacking the nitro group. If toluene is the reactant attacking the nitro group because one of the positions that starts to form a positive is tertiary, it can stabilize the positive more through hyperconjugation and induction. And so that goes through a lower energy transition state. And the intermediate is lower in energy because the intermediate also has a carbocation that forms, and one of those positions that carbocation is shared over through resonance is tertiary versus secondary. And if I were working with benzene here instead of toluene, all three positions would be secondary. So that would be less stable with benzene versus with toluene. So this explains what we were talking about here. The lower transition state energy means that when I have toluene, the reaction occurs 25 times faster because the transition state is slightly lower in energy, and those slightly higher percentage of the collisions occur have the necessary energy to produce the intermediate. So that also helps to explain why the nitro group ends up connecting to that position versus the other position. When the nitro group is attacked by the ortho position, it goes through a relatively stable transition state and produces a relatively stable intermediate because of the positive charge forming there on a tertiary site can be more stabilized through resonance, through hyperconjugation and induction than it can on a secondary site. So how is that? It's through hyperconjugation and induction. Is the transition state also affected? Yes, right? So we just talked about that. So in the intermediate, it's a full positive. In the transition state, it's only a partial positive, but whether or not that positive is on a secondary versus a tertiary carbon does make a difference. So one pathway occurs more often than the other. So let's take a look at the pathways for the meta and para attack. So if this carbon starts to form a new bond with the nitrogen there, we're looking at the meta position starting to connect. So we would want to look at what the transition state looks like. So again, we would have this bond breaking, the new bond forming, some partial charges forming here and here. And due to resonance, the partial charge that forms in the ring would immediately be shared over 3 carbons. But what I'm noticing is all 3 of those carbons are secondary. And we see this positive at the same carbons in the intermediate. So the transition state and intermediate aren't really stabilized by having the methyl group there. Right, we just saw over here how the methyl group stabilizes the positive charge in one of the key resonance contributors and in the transition state. So if you don't have the methyl group there, we were saying with just benzene, then the partial charge exists on only secondary carbons. It's not as stable, so it's higher in energy. So we end up with a similar situation here. Due to the Metaattack, the way it works out, and the positions where the positive is distributed, both during the transition state and during the intermediate, the methyl group does not help to stabilize that because the positive never ends up on the carbon that the methyl group can help shift electrons toward to stabilize. Conversely, with the para attack, we look at the transition state there. As the pi bond breaks, starts to form a new bond with the nitro group in the para position. Due to resonance, the partial positive is going to be spread out over 3 carbons, but this time it does happen to immediately exist at the para position. So the para attack has a resonance contributor during the intermediate and during the transition state that has some extra stabilization due to the methyl group being able to shift electrons in through induction and hyperconjugation to help stabilize that positive. So when we look at the transition states, the Metaattack is very similar to benzene. So this is like the intermediate, and the positive is spread out over 3 carbons, but all 3 of those carbons are secondary, just like it would be for benzene reacting with the nitro group. And so since the methyl group does not help to stabilize that, if anything, it only helps to destabilize it a little bit through sterics, although that would be quite minimal. But that's going to be relatively high in energy. It's not going to happen nearly as often. So the amount of product that results from that regio selective, that regio outcome is going to be quite minimal. So looking at the ortho versus para, their transition state energies are pretty close. The ortho's a little bit higher, and that's due to some sterics, right? So if the new group coming in is on the very next carbon from the methyl group, and they're in the same plane due to the ring being flat, it's going to create some sterics there. And so that's why that one's slightly higher in energy than this one. But despite it being slightly higher in energy, as we were saying before, there's a statistical likelihood for it to connect at the ortho position just randomly, because there's 2 of those positions. That should occur twice as often as the connection at the para position. So if we look at the percentages, though, what do we see? It's not quite twice as often, right? If there are no energy difference, I would expect the ortho position to happen twice as often as the para, and the result is twice as much product. But it's not twice as much. And that's because some of the statistical advantage at the ortho position, because there are 2 of those positions versus only 1 para position, is offset by the energy difference between the reaction pathway going through a slightly higher energy for the ortho reaction versus the para reaction at slightly lower energy. Now, if this group were much bigger than a methyl group, and it were blocking sterically a lot more, then you'd see a much bigger difference here. And then the para position might actually be the one that gives you the major product. So there's definitely some sterics associated with that reaction that you want to keep in mind when you're thinking about the regiochemical outcome and the relative rates due to the relative energies of the transition states. All right, so let's look at a different group attached to the ring. So what we said about this methyl group pretty much applies to any alkyl group, but you do want to keep in mind the bigger the alkyl group, the more sterically hindering it is, the more of an impact that's going to have on the transition state here, and the more likely the para connection is going to be versus the ortho connection. The meta connection is really going to be negligible. For the most part, if you have an alkyl group, which is just a hydrocarbon group with all single bonds, so like a methyl, ethyl, propyl, isopropyl, butyl, isobutyl, secbutyl, etc. The more sterically hindering that is, the more the para will be favored versus the ortho. But if it's just a methyl group, due to the statistical likelihood of there being two ortho positions versus one para position, the two ortho positions give the same product, that is going to happen a little bit more often and become your major product, right? So that's what you'd want to think about in a reaction like that. So, other groups that could be attached to the ring that would affect where the next EAS reaction is going to occur. One of those groups, one of those types of groups is an alkoxy group. So a specific example of that would be methoxy. So if I have a methyl here, it's a methoxy. If I have an ethyl here, it's an ethoxy. Any other alkyl here makes this an alkoxy group. But putting the oxygen directly connected to the ring has a big impact on this reaction because the lone pair of electrons on the oxygen can shift in through resonance and create some of these minor but significant resonance contributors. And since these resonance contributors have a little partial negative at the ortho and para positions to that methoxy group, then whatever electrophile I add, it's more likely, I can imagine, that it'll be the ortho or para positions that are starting to attract to and connect with the electrophile. So I expect the methoxy group to do the same thing in terms of being an ortho para director instead of directing the new electrophile to come into the meta position, because the meta position doesn't have any extra partial negative in any of these resonance contributors. The structure that contributes most to the resonance hybrid is going to be the one with no formal charge, right? So that's, you want to keep that in mind. The formal charges here make this pretty unstable. So these three contributors are pretty minor compared to the original structure with no formal charge, but they're significant enough to help create slight amounts of partial negative on that carbon that will attract the electrophile in. In fact, they're so activating due to that resonance that bromine can be reacted with this ring without the need for a Lewis acid catalyst. And the reaction goes so well, it's hard to prevent it from happening at all of the available ortho and para positions. So if you want to install bromine at each of those positions, you'd use excess Br2. If you only want to install the bromine at one of those three positions, it's really not possible to do that very easily, because once the bromine is connected at one position on one molecule, and it could be ortho or para, that molecule could react again and install another bromine before another new unreactive molecule has a chance to even put one bromine on the ring. So you'd end up with a mixture of some molecules not having a chance to react at all, while others might have one or two, and some might even have three bromines attached, even if you didn't use excess. So if you want to put a bromine at every ortho and para position, this reaction works nicely. Great yield, obviously. But if you want to install it selectively at only one of those positions, it's not going to work because this group is too activating, and you can't control which of the positions it reacts at. It stabilizes the transition state really very nicely. So let's take a look at that. So for the ortho or para attack, those are quite similar. What's going to happen here, I'll just draw the ortho one. You can imagine the para is going to be very similar. So I've got anisole here, minus the pi bond that should be here. So this pi bond is going to break and is going to connect to the nitro group. Just use the nitro as our electrophile in this example. So what we were saying before is, once the electrons get pulled away from one of these carbons to make the new bond, that carbon starts to take on a partial positive. And then we're saying, well, these electrons could shift around and help to spread that partial positive out over multiple atoms. And since the oxygen has a lone pair right there, it can also push the lone pair in and start to spread that partial positive to the oxygen. So spreading out the positive that forms on the carbon over more atoms really helps to stabilize it. And you can see that in the transition state here. The transition state down here would look very similar. And you can also see it in the intermediates. If the reaction occurs at the meta position, and that starts to pull these electrons out, then the partial positive won't form on the carbon that the oxygen's connected to. So there's no way for the oxygen to shift electrons in through resonance. The oxygen's ability to share electrons to stabilize the positive through resonance is not possible when the attack occurs at the meta position due to the way that the electrons work out. So the reaction should be occurring much more often at the ortho and para positions when I have a alkoxy group connected there, because when the reaction occurs at the ortho or para positions, the transition state is stabilized through extra resonance with the lone pair from the oxygen, and the intermediate is also stabilized. And in this case, these are the major contributors. It's more stable to put a positive on an oxygen and make all the noble gas configurations for all the atoms than to have it on a carbon which has an incomplete noble gas. So not only does the transition state and intermediate have more resonance when the reaction occurs at the ortho or para position, it's also the most significant resonance contributor, which really helps to stabilize it. So when we look at the reaction coordinate diagrams for the nitration of anisole, we see a much higher energy for the Metaattack versus the other. So it's not like there's something that's making this unstable. It's just that the extra resonance from the oxygen is really helping to stabilize the other two, making them significantly lower in energy than the Metaattack. And again, the reason the ortho transition state is higher than the para one is because of the resonance, or the sterics between the groups there when they're close together. So we have this competition now between the ortho being more likely statistically, because there's two possible positions where the nitro group can connect to give the same exact ortho product, versus one position where it can connect to give them para product. That's kind of in competition, favoring the ortho product, competing with the idea that the para product doesn't have the steric hindrance, making it less stable during the transition state. So it will happen more often simply because the transition state is lower. And so what we see in this case is the para product is a major product. So the difference in this transition state energy here versus here is a big enough difference where the lower energy transition state happens more often, specifically because of the sterics. And so I just want to contrast that with what we saw over here. When I have a methyl group, it's not as sterically hindering. If I put an extra oxygen there and I put an OCH3, the OCH3 pushes the CH3 out a little bit, and when it's swinging around as it rotates, it creates more sterics. So there's not a very big difference in energy when I have a methyl group there in terms of the sterics versus a methoxy. And methoxy is a little bit bigger, it swings around more like a propeller, and it's going to create more sterics there. So that's why there's a bigger difference between these two, and that's why the para pathway is the favorite pathway really for any alkoxy group. If I made the methyl into an ethyl or propyl or larger, then this difference would be even more pronounced, because that would create even more sterics with any incoming electrophile at the ortho position. So even though it's stabilized by resonance, the sterics would kind of destabilize it compared to the reaction at the para position. All right, let's take a look at another group. So we've covered alkyl groups and alkoxy groups. Let's look at what if a nitro group is already connected to the ring. Right, so for a nitro group, we kind of see the opposite of what we just saw. I just want to contrast that real quick with what we just talked about. When we talked about the alkyl group, we said when electrons start to leave the ring and get connected to an electrophile, the alkyl group, through induction and hyperconjugation, shifts electrons in there to help stabilize the positive that forms both during the transition state and on the ring, and that helps it occur more readily through induction and hyperconjugation. When you have an alkoxy group, then it's the oxygen that shifts electrons in through resonance. So we've been seeing these factors throughout last semester and this semester, and what we've seen, we recognize that resonance is usually a more significant factor than induction and hyperconjugation. So if we were to look at the relative rates of reaction for toluene reacting with the same electrophile that anisole might react with, anisole would react a lot more often because the resonance really helps to stabilize the positive that forms during the transition state intermediate more than an alkoxy group would, or I'm sorry, an alkyl group. So in this case, though, we're looking at a nitro group, right? And both of these groups are pushing electrons into the ring, whether it be through resonance or hyperconjugation and induction. But when a nitro group is attached to the ring, it's going to look a little different. Oops, what happened here? Get a little bit more space there. Oh, I can't do that. Oh, well. So let's take a look at the nitro group. What effect does having a nitro group mean for the ring? So if a nitro group's already there, it's going to look like this. Oops, no, it's not. Can't have a 5-bonded carbon. That would be crazy. So my nitro group has a double bond on one side and a single on the other. So the nitrogen won't have more than 8 electrons around it. But it withdraws electrons through both induction and resonance. And while the resonance is a more major factor, these factors both are making this ring less electron rich. Right? The full formal positive on the nitrogen and it being more electronegative than carbon means it's withdrawing electrons through induction. Right? This cloud of electrons shared between the carbon and the nitrogen is shifted more toward the nitrogen, creating a lot of partial positive here, and that attracts these electrons and creates some tiny partial positives there. And so when we're talking about induction, that impacts things right close to the area where there's a big electronegativity difference or charge attracting electron. The resonance occurs because of the NO double bond here. Because there's resonance here where these electrons can shift away onto the oxygen since it's more electronegative than nitrogen, that allows for the nitrogen to take on even more positive charge and actually attract electrons from the ring out there to complete the noble gas configuration for that nitrogen, which pulls electrons away from this orthocarbon. And then those could shift over and pull some away from the para, and then those could shift over and pull some away from the other ortho. So in this structure, due to the induction and resonance, the ortho and para positions already are carrying significant quantities of partial positive. So if you're going to react this with an electrophile to do another EAS reaction, the electrophile is not going to come in and be attracted to and connect to carbons that already have positive charge. So that's why we see the nitro group is a meta director. It will direct a new electrophile into the meta position. But when it does so in a way that deactivates the ring. How does that deactivate the ring? Well, it means that all the transition states here are pretty high. None of these reactions are going to happen very often because all these transition states are quite high, especially the ortho and para. So the reaction will occur at the meta position more often because it's a lower energy transition state. But when we say it's deactivated overall, what that means is if the nitro group weren't there at all, and we just had benzene, and we wanted to react benzene through this nitration reaction, it would go through a lower energy transition state and intermediate than the molecule that already has one nitro group attached. And so even though the meta attack occurs more often than the ortho and para, it still doesn't occur very often, and it still occurs less often than the reaction would occur if there were no substituents on the ring. And that's because the nitro group withdraws electrons. It attracts electrons out of the ring through induction and through resonance, creating partial positives on the ring at those positions specifically. So oh, cool. That is such a great question. Yeah. So what she's asking is, since this nitro group withdraws electrons and creates positives on the ring, what about the ring reacting with the nucleophile instead of an electrophile? Right, so obviously that wouldn't be an EAS reaction because E stands for electrophilic aromatic substitution, but there is such a thing as an NAS or nucleophilic aromatic substitution. And in order for that reaction to work, the ring has to have at least one highly electron withdrawing group like a nitro group. And that's a great point to make because that nitro group will attract electrons out of the ring, creating partial positives that can then attract, if the nucleophile is strong enough, it can attract the nucleophile into one of those positions. And when that occurs, the nucleophile will attack positions that are ortho or para to the nitro because those positions are more positive due to the resonance of the nitro group withdrawing electrons through resonance, specifically from the ortho and para position. Great point. So here we're still talking about EAS, though. We will talk more about that NAS reaction later in time. We'll look at some details relating to that. So, question here. Withdrawing electrons from the ring deactivates it how? Because it creates partial positives on the ring that repel the positive of the electrophile. When the electrophile attacks or is attacked, it creates positives on the ring. So if the nitro group's already there and it's pulling electrons out and it creates positives, then that causes more repulsion, so it's less likely to occur. Right? So that's why all three of these reactions go through relatively high transition states, because in each case there's some positive on the ring and additional positive on the ring created by the nitro group, and that causes at least some repulsion. The closer those positives are, the more repulsion is created, right? That's why the ortho and para go through significantly higher energy transition states than the meta, because in both the ortho and the para, as the electrons are moving out of the ring, it creates a partial positive that through resonance exists specifically on the carbon that the pre-existing nitro group was already located at, because that carbon has a lot of partial positive as the nitro group pulls electrons out, putting a positive right on that site is going to be especially unstable. And so that's why we see those transition states and intermediates especially high in energy for the ortho and para EAS reaction. And that's why if we have a nitro group or other electron withdrawing group on the ring, it should pretty much always direct the next group to end up in a meta position, specifically to avoid the high energy extra repulsion that occurs during the transition state whenever that positive is existing on a carbon that's directly attached to the electron withdrawing nitro group. Will withdrawing electrons make the transition state or the intermediate less stable? Yes. Right? That's the whole point we're just saying. By withdrawing electrons, it makes the transition state less stable. It makes each pathway occur less often, especially the pathways that produce these specific intermediates that are especially unstable due to the electron withdrawing group putting all that extra positive all right on the same carbon, making that an especially unstable area of positive charge. All right, so with that knowledge, let's see if we can figure out how to make this product. So we know now that once we put an electron withdrawing group on the ring, it's going to direct another group to end up meta to it. So specifically, if you want to install two groups on a ring, right? Obviously we don't have any groups here. We want to put both these groups on. We have to make sure that they're put on in the right order. You can't connect the nitro group here first because as an electron withdrawing group, it would, as we just explained why, direct the next group to come in at one of these positions that's meta to the nitro group, and that's not what we want. We're looking for this regiochemical outcome where the two groups connected to the ring are para with respect to one another. So I don't want to add that first. And I want to add this other group. What we were saying before spring break about adding this group is, while it may seem like a good idea to do an Friedel-Crafts alkylation to try to get this ring to come out here and push out the chloride, and this is not a very good electrophile yet. It doesn't really have much of a positive at that carbon to attract the electrons from the ring. So the chlorine could leave, but that would produce a really unstable primary carbocation. So it won't do that on its own. What would be likely to happen would be for it to leave, and then as it's leaving a hydride shift, that would produce a tertiary carbocation. And then the ring would attack that, and I would end up getting a tertiary group there after re-aromatization. But that's not what I want. So we don't want to do an alkylation here. We want to instead set up an acylation. Right, so we want to install 4-carbon group. We want carbon 1 to be the one that connects. We don't want any rearrangements. So we'll turn this into a CO double bond with the Cl. That, along with the aluminum chloride Lewis acid catalyst, will help attract the chloride leaving group, create a carbocation there. They'll be stabilized through resonance with the oxygen. That will produce what we called last time an acylium ion. And the resonance there will attract electrons out and make a positive there. So that will attract the ring to connect to that site. And once it re-aromatizes, we'll get this as our first intermediate. So then the question is, do I want to reduce the CO double bond down to a CH2 first and then install the nitro group? Or do I want to install the nitro group first and then reduce? And the answer is you don't want to try to install the nitro group first, because this is also a meta director. It's similar to the nitro group we looked at over here, in that because the CO double bond through resonance electrons can shift out here and create a positive here, that can allow these electrons to shift up. So this will put a lot of positives specifically in the ring. And if I make an NO2 electrophile for that to attack, it's not going to be likely to attack it at one of these positions that's already carrying positive, because the NO2 is positive. And I would end up getting the NO2 to connect meta to the carbonyl, which is not what we want in the end. So the next step here, we would want to reduce the CO double bond to CH2. And so we could do that with zinc and HCl. That would reduce the CO double bond to a CH2. So that's Friedel-Crafts acylation followed by reduction of the CO double bond. Now we have an Orthopara director. Now it's actually donating electrons to the ring through induction and hyperconjugation, but it's so sterically hindering we don't expect much reaction to occur at the ortho position. So that's why we would expect, if we add the conditions to install a nitro group, that would occur at the para position. So predicting what's going to happen here, understanding the order in which the reactions need to be done, really relies a lot on you understanding the mechanisms and the reasons for why things end up connecting where they connect. So if you have questions about that, please let me know. And if you're practicing, I can always check. I'm happy to check over your work for you. All right, so let's make some general statements here that will help us moving forward. If you can tell that a group donates electrons, it's always going to be an orthopara director for the reasons we discussed. And then if you can tell that the group is withdrawing electrons through either induction or resonance or both, that's going to be a meta director, except if it's a halogen. So the halogens are a little bit special, and we'll talk about those specifically in a minute. So when I have a halogen present, it is withdrawing electrons through induction. Right? We know that chlorine, bromine, fluorine are all significantly more electronegative than carbon, and they all will create some partial positive there. So the ring has some partial positive. And when the chlorine is pulling electrons away and creating that partial positive, it repels the positive that's already there. It repels the positive that forms during the transition state and in the intermediate. It's already there on the picture, but it forms during the transition state and the intermediate. And so that extra positive, because the chlorine is electronegative and pulling electrons away, that positive repels this positive that forms during the transition state and during the intermediate. And that makes the whole thing happen less often, because that repulsion increases the energy of the transition state, and fewer of the collisions that occur will have the energy necessary to get through that reaction. So it's slower than it would be if benzene were reacting. Putting the chlorine group on the benzene to make chlorobenzene slows down the reaction. And in every other group that slows down the reaction or deactivates because it withdraws electrons, every other group is a meta director, but the halogens are orthopara directors, and that's because of resonance. So the induction slows the process down and controls the kinetics for the most part, but the resonance controls the regiochemical outcome. And that is because if the nitro group ends up connecting ortho or para during the transition state and in the intermediates that you can see here, there's some extra resonance that the halogen can engage in to help stabilize that positive over a greater number of atoms, 4 atoms, versus if the new incoming electrophile connects at the meta position, the positive never really forms on the carbon the chlorine's connected to, so there's no way for the chlorine's lone pair to help stabilize that positive through resonance. So we end up in a situation where the group is an orthopara director due to the resonance that occurs there, but it's also a deactivator because of the positive it puts into the ring more positive than it puts in negative. All right, so let's see if we can look at some energy diagrams. So I want to look at nitration of benzene, orthonitration of chlorobenzene. And so if we're looking at the energy diagram, mostly we want to focus on the transition states. So let's just draw a couple quick transition states here. So I've got benzene. It's going to break a pi bond and form a new bond with a nitro group since we're nitrating the benzene. And that's going to create a partial positive here, which through resonance can be spread out over 3 atoms. So this looks pretty good. There's nothing else on the ring already to stabilize or destabilize those positives. So that's kind of like a middle of the range amount of energy necessary to get to that transition state and the first intermediate that would form. Right? We're just focusing on the slow step of the mechanism, not the whole mechanism, because it's the kinetics that determines the regiochemical outcome. So what if we looked at nitration of chlorobenzene? So let's imagine we had a chlorine here already, and this bond breaks. It starts to form a new bond to a nitro group at the position that's ortho to where the chlorine was initially. As the electrons get pulled out, it would form a partial positive here. These electrons could swing over, and that would form some other partial positives. So if we were looking at the stability of this occurring, we have to keep in mind that the chlorine is an electron withdrawing group. Its electronegativity attracts electrons away from the ring, creating extra partial positive there. So that's only going to make it less stable. If we put more of the same charge on the ring's going to become less stable. So if we were to look at that energy diagram, that would go through a higher energy transition state and a higher energy intermediate. So let's compare that to metanitration and paranitration. So for the metanitration, we'll call this C. I've already got chlorine on here. If the nitro is going to connect to the meta position, it's pulling electrons away from this carbon. So these can shift over there. These can shift here, positive there. So how does that compare? C versus B, what's the difference? Well, when the chlorine pulls electrons away, it's going to create a partial positive there. So yeah, I got basically the same amount of partial positive in the ring on both. This one has a disadvantage that I've got lots of positive all in one carbon, but I can't forget that the halogen can also donate electrons through resonance. So by shifting electrons in there and helping to share some of that positive onto the chlorine, that would really diminish the amount of positive right on that carbon. So in this case, spreading the positive over multiple atoms is going to be a little bit more stable than having it only on 3 atoms in the ring versus also including the chlorine. Right? So I'd have larger quantities of positive here Over here, the positives on the ring would be less because they'd be sharing some of that positive with the chlorine. So C should be even higher in energy. The reason C is higher in energy than B is because B is stabilized by a little bit of extra resonance with the lone pair from the chlorine. That can't occur here because the positive doesn't exist on the carbon that the chlorine could shift electrons into. And if we looked at para, that would look something like this. These electrons would break. They would come out here to form a bond with the nitro group, creating a partial positive here. Electrons would swing in. So here is another example where I get the partial positive right on the carbon where I need it for the chlorine's lone pair to help stabilize that and spread some of it out. The chlorine through induction, though, is withdrawing electrons, creating more positive. So it's still less stable than it would be if the chlorine wasn't there. The induction of the chlorine creates extra positive in the ring, repelling the positive that's already there, making it less stable than it would be if it were just benzene. But it's more stable than it would be if it were meta, because at least the lone pair can shift in there and help to stabilize some of that positive through resonance. So we can say that D, we'll just call this D, D is higher than in energy than A and lower energy than C. Well, how does D compare with B? Well, there is also a slight steric hindrance between these groups when they're on adjacent carbons versus if they're on opposite sides of the ring. So because D wouldn't have any extra sterics associated with the crowding of those two groups since they're so far away from one another, D would be somewhere in here. And so you should be able to rank the likelihood of different pathways once you consider the induction, the resonance, and the sterics associated with each of the transition states. All right, so that gives us a pretty good idea, hopefully, of the different effects of the different groups on the ring on a subsequent EAS reaction that would occur to that ring. And so let's summarize some of the things we saw and add in some other groups to give us a more comprehensive view of what we might be expected to deal with. So when you have a group attached to the ring that has lone pairs right there on the very first atom out from the ring, the more willing those lone pairs are to shift into the ring through resonance onto the carbons or onto the partial positive that would be formed when this ring reacts with an electrophile, the more stabilizing that group is going to be during the transition state, and the faster that reaction is going to occur. So these are called strong activators. Because they're so good, what makes them so strong? They're so good at resonance. They're all excellent at shifting electrons into the ring to stabilize the positive that forms during the ring, in the ring during the transition state. This one is really good, right? It's a full negative. So it really is very good at shifting electrons in there to stabilize the positive that forms in the ring. And nitrogen's less electronegative than oxygen. So when you have a nitrogen here, it's very willing to share its electrons in there as well. So, that's what you want to think about there. Moderate activators, what makes them moderate? Well, they have the same feature as strong activators, which is a lone pair that can shift in through resonance into the ring to help stabilize any positive that forms in the ring. The difference is there is also an extra resonance for the first three where that lone pair can also shift out here. So the lone pair is not available to stabilize positive on the ring to make this reaction happen more readily if it's also engaged in resonance outside the ring. Right? So none of these lone pairs are engaged in any resonance other than the resonance with the ring. So they're really able and available to stabilize the positive that forms on the ring during the transition state and intermediate. These ones are as well, but just not as much, which is why they're only moderately activating. All of the groups on both of these categories are orthopara directors, because they specifically, through resonance, will donate electrons in and stabilize the structure a lot more if the new electrophile comes into the ortho or para position rather than the meta position. And so what's the difference between this one here and this one here? They are they look very similar. Well, the difference is I've got an R group here, obviously, instead of a hydrogen. And so what that does is it creates a situation where this is going to have a fair amount of sterics versus this one, right? The OH group is small, so it doesn't block anything coming in to the ortho position specifically. But the R group here, even if it's a small methyl group, it's going to block the ortho positions a little bit. If it's a larger group, it's going to block them a lot. And so that the sterics that occurs during the transition state there is going to slow that one down a little bit compared to the OH, which is why it falls into the moderate activator category instead of the strong activator. We said and saw how the methyl group weakly activates the ring, or it speeds up the reaction due to its ability to share electrons through hyperconjugation and induction. But since hyperconjugation and induction aren't as major factors as resonance, they just don't shift as much electron density into the ring. So when any of these rings react by picking up an electrophile, which is going to create a positive charge on the ring, that positive isn't going to be as stabilized by these groups as it would be by a group that can shift a lone pair in through resonance readily. These are also orthopara directors. And so another category of weak active deactivators. Okay, so these are deactivators, obviously, right? The deactivators deactivate because they withdraw electrons from the ring. Right, so the activators push electron density in there and create some partial negative. And that helps to stabilize the partial positive that forms when the electrons swing out to pick up the electrophile. Since these on net are electron withdrawing, they create a little bit of partial positive on the ring. More partial positive if the element's more electronegative, but then that partial positive will repel the electrophile, and so the reaction goes through slightly higher energy transition state. So what makes them deactivators is withdrawing electrons. What makes them weak deactivators is that even though they withdraw electrons through induction, that is offset somewhat by their ability to donate electrons through resonance, which would otherwise activate the ring. So this is a rare situation where induction and resonance are competing, and induction becomes a slightly more major factor than the resonance. Normally, resonance is a more major factor. Normally, we would say, well, if an atom can donate electrons through resonance, it's going to push more electron density into that ring than it would pull out through induction. But the halogens are just not very good at resonance. They're not very good at stabilizing a positive. They're not very good at shifting electrons in. So for fluorine, it's not good because it's so electronegative. It doesn't do a very good job of sharing an extra pair of electrons. And for the other ones, they're not very good at shifting electrons in because the orbital overlap isn't very good. We've said this before, where if you have a second energy level atom like carbon trying to overlap a p orbital with a third, fourth, or fifth energy level halogen, then the halogen's orbital is going to be farther out from the nucleus. There's a mismatch in alignment there, and the orbital overlap's not very effective. So these ones can't donate electrons through resonance very well, which is why they don't push as much electron density in through resonance as they pull out through induction. So that makes them deactivators but those two factors are offsetting somewhat, so they're only weakly deactivating. The moderate deactivators all have, for the most part, CO double bonds with a couple exceptions, but all of these have the same feature, and that is some electron density can shift away from the ring through resonance, and that creates a significant positive here that can pull electron density out of the ring. And so this is a pretty major electron density being pulled out of the ring, creating a lot of positive there, and that's only going to make it less stable when it starts to connect to an electrophile. All that positive is going to cause a lot of repulsion. So these reactions are less likely to occur. They're higher in energy during the transition state due to the extra positive that causes repulsion. But they're moderate because they're not extremely strongly pulling electrons out of the ring, right? These are all minor resonance contributors. Right? CO double bond, for the most part, it doesn't, the electrons don't shift up to the oxygen. It's a minor resonance contributor. So it occurs, but in a minor way. And so it doesn't create a huge amount of positive to pull the electrons out. The nitro group is more strongly deactivating because the nitrogen is carrying a full formal positive. So in addition to the resonance, there's also a lot more induction for the electrons being pulled away here. So if I have a formal positive on this nitrogen, even though there's no resonance to pull electrons out of the ring, through induction, it really strongly attracts electrons, and that creates a very large amount of partial positive on the ring that kind of repels the electrophile as it attacks. And during the transition state, the extra positive makes it less stable. So these really are difficult, and this one here, because these halogens are so electronegative, that creates a very large partial positive on the carbon, which attracts electrons out of here. Also through resonance, these R groups are blocking things, so depending on the size of them, that is a minor factor. But these ones will very slowly react through an EAS reaction, and potentially it could be too slow for the reaction to be practical. So that's another consideration. All right, so one group that you might have to deal with is an amide. Some amides are orthopara directors, and some are metadirectors. It depends on which way the ring is flipped around. And so we could talk about this example, but it makes more sense to probably just talk about the quiz question, since the quiz question included both types of amides. So an amide is a functional group where there's a nitrogen connected to a CO double bond. And there could be an R group or a hydrogen here. There could be an R group or a hydrogen here. And there could be an R group or a hydrogen here. So this is the amide functionality. And what makes an amide is that the nitrogen is directly bonded to the CO double bond. And so those electrons can shift in through resonance. There's a minor resonance, but significant resonance contributor where there's electron density shifting up to the more electronegative oxygen. So the aromatic ring could be one of these two groups directly connected to the nitrogen, or it could be this group directly connected to the CO double bond. And so whether or not the amide group is an orthopara director or a meta director, it depends on which way it's flipped. And so if you're familiar with the mechanism, you don't have to memorize anything here. You'll recognize that if the nitrogen is directly connected to the ring because it has a lone pair, even though it's slightly engaged in resonance here, the lone pair could still shift in and push electrons to the ortho and para positions and make those positions more likely, because it'd be slightly negative, to pick up an electrophile like an NO2 positive that would be created when nitric and sulfuric acids react with one another. So here, due to the sterics as being pretty significant, I would expect for sure the major product to be the one where the nitro group ends up connected at the para position. And so, well, why is that again? It's because during the transition state, when the electrons start getting pulled out of the ring to connect to the nitro group, and they get pulled away from this carbon, not only is there resonance to help stabilize that positive here and here, there's also resonance from the lone pair to help stabilize that positive and spread it out also onto the nitrogen. So there's an extra, very significant resonance contributor that stabilizes the positive that forms during the transition state and intermediate and allows it to go through a lower energy transition state and intermediate, specifically when the nitro group attaches to the para position. It's also lower in energy than it would be at the ortho position due to sterics. So I would still get the same resonance contribution from this lone pair if it connected at the ortho position, but the sterics is kind of blocking that. With the other connectivity, where the CO double bond is connected to the ring, I have the opposite situation. This lone pair is no longer close enough to the ring to be donated in there through resonance. And instead, the resonance it can do is to move up, in here and push electrons up to the oxygen. But when electrons swing up to the oxygen, creating a positive here, these electrons can also swing out. And so that only creates positive on the ring. Oops. And so that's a deactivator. And deactivators, with the exception of halogens, will promote the next electrophile to connect to the meta position. And the reason for that is because when we look at the transition state, if the reaction occurs at the meta position, it will pull electrons away from the other carbon there. So you might say, well, the para position has less sterics. Why would it go to the meta position? Well, the idea there is this oxygen is pulling electrons out, creating a big partial positive here. So as long as I can avoid the positive in the ring existing right next to that, I'll be able to avoid some stability. And it'll happen through a lower energy transition state and being more stable. And that's what we get. When the nitro group connects at the meta position, pulling electrons away from this carbon, it creates a partial positive here. When these electrons swing over, that goes there. And when these electrons swing over, it goes here. So I'm kind of spreading the positive out instead of putting it all right next to one another. And that helps it to go through a slightly lower energy transition state, occur more often. And that's why I get the major product resulting from the reaction occurring at the meta position. Oops. Let's redraw that. So we get the para product due to sterics over the ortho product, but the ortho and the para would be much more likely to occur here due to the electron donation, whereas in the bottom reaction, I expect a meta product due to the electron withdrawing nature of that amide when it's positioned with the CO double bond group directly connected to the ring. All right, what about this reaction? Well, sometimes you already have groups connected to the ring, and you have to think about how those groups are affecting the ring electronically through induction and resonance and potentially hyperconjugation. And so what we'd see here is we talked about the methyl group. We said, oops, I drew that arrow the wrong way. The methyl group is donating electrons into the ring through induction and hyperconjugation. And so that's why it's usually an ortho para director. The para position is already occupied. So I would expect the methyl group to direct a new substituent into one of those two positions. I would not expect the methyl group to direct a new group to one of the meta positions that are meta to it, because if it did, then the positive wouldn't exist on this carbon where it can be stabilized through hyperconjugation and induction. But I don't just want to consider the effect of the methyl on the ring, I also want to consider the effect of this nitro. And we know the nitro group being so strongly electron withdrawing is going to direct a new substituent meta to it, which is the same position where the methyl group's directing. So a lot of times you'll have groups working in concert where they're both directing the new group to come into the same spot. And so it's easy to predict that the new group will end up either here or over here, which would be the same structure just flipped over like a pancake. And as we said, the nitro group specifically is deactivating positions that are ortho and para to it. The para position is already occupied. The position is para to the nitro. But these two positions here are ortho with respect to the nitro. And we said we don't expect the nitro group to allow a reaction to occur ortho to it, because as it withdraws electrons, that specifically puts a lot of positive at those positions. And that will not attract in an electrophile to those positions. And also during the transition state, there's going to be more positive concentrated in one place repelling if the new group comes in there, as we saw previously. So both groups direct the bromine to come in at the same spot, which is either here or here, and that's the same things due to the symmetry. So here we have another example. This one's a little bit trickier because we know the OH is electron donating through resonance, and the methyl is electron donating through hyperconjugation and induction. But the resonance here is going to be more significant. And so we have to allow the OH to be, since it's a stronger, we'll just go back here and show that, the OH is one of our strongest activating groups, versus a methyl, which is weakly activating, because the hyperconjugation and induction are not as significant as resonance. So we expect the oxygen, as its lone pair gets shifted into resonance, to direct the new nitro group to positions that are ortho or para to it, and the para is already occupied. We expect the methyl group to direct the new group into positions that are ortho and para with respect to it. The para is already occupied. So this OH group is strongly directing the new group here, and the methyl group's only weakly directing the new group there. So we definitely expect the resonance to take priority there, and would predict that the major product at least would have nitro groups mostly connected here or over here, but again, those two positions are equivalent due to symmetry. So here I've got a couple groups that are both weakly activating. This one's directing the new group ortho to it. This one's directing the new group ortho to it. So what's the difference? Well, the difference here has to do with sterics. Right? So this group's a little bit more bulky, so it's kind of sterically blocking these two positions versus the methyl group being much smaller. So that's why I expect the major product to put the nitro group next to the smaller group, rather than the one where steric endurance would be an issue during a transition state. So if two groups are similarly activating, but they're not predicting the new substitution to occur in the same place, then you would look at sterics to see which space is more open. Similar situation here. This larger group is still an activating group. It's still donating electrons through induction and hyperconjugation, specifically activating positions that are ortho and para to it, and the para would be activated much more than the ortho due to the sterics. This methyl group isn't sterically hindering, but it's also an activator due to induction and hyperconjugation, and it's highly activating the groups ortho and para to it. Whenever a position is ortho to two different groups, usually the sterics is going to block that out. So even though the methyl is kind of small, since this position here is sandwiched in between the methyl and the isopropyl group, there's a significant amount of sterics there. And so I don't expect the reaction to occur there much. Right? So I'm not really seeing that. And if I look for it, it's not really observed due to sterics. So I wouldn't expect a new group to add between two carbons that are already having significantly sized groups located there. So then it comes down to a competition between this site here and this site here, and they're equally activated by both groups electronically. The difference again is sterics, right? There's a little bit more sterics over here between the larger groups. So this would be the major product and this would be the minor. Right? So this is tricky. It takes a lot of practice for you to get to the position where you can predict what the major product is going to be, because there's a lot of factors involved. You got to look at resonance, you got to look at induction and hyperconjugation, you've got to look at sterics, you've got to recognize that some groups are more strongly activating or more strongly deactivating than other groups, the strong groups, the weaker groups, the moderate groups, and they're all going to impact where this new group's going to end up connecting. Sometimes you want a new group to come into the position that's not necessarily the most likely position for it to go to. So here's an example of that situation. Here you've got a terp-butyl group already connected to the ring, and we want to connect a bromo right next to that. But we know the terp-butyl group through induction and hyperconjugation is an ortho para director, and since there's so much sterics associated up here, the first group attached is pretty much always going to go in the para position. And so last time we talked about a specific group that can be installed and removed, and we can consider that to be a blocking group. And so the idea here is, since this terp-butyl group is going to direct the next group to come into the para position first, we could block that by installing a group there through an EAS reaction. Since that's the most likely site for the next reaction to occur, we'd install the group there, then do the bromination so that it can go to the position we want, and then remove the other group, and then we would have our product. Right, so here is a specific example of how to do that. We said we can install a sulfonate group by using the fuming sulfuric acid, or we can remove it and replace it with a proton by using dilute sulfuric acid. This is a reversible process depending on the conditions we're using. And the sulfonate group, if we just take a quick look at its structure, this sulfonate group is going to look like this. So is that activating or deactivating? Is it an orthopara or meta director? Well, it's got something like a CO double bond. It's got an SO double bond. It's very similar. These electrons can shift out here and start pulling electrons out of the ring. So it's not as bad as a nitro group, but it's similar to a CO double bond. It's a deactivator and it's a meta director, which is actually exactly what we need in this situation. So what's happening here is I've got the terp-butyl group already installed. I'm going to use this fuming sulfuric acid to install the sulfonate group. Now the sulfonate group is a meta director, so it's going to direct a new group to come in here. The terp-butyl group is an orthopara director because it's donating electrons rather than withdrawing them. And that also will direct the Br2 to come into the same site. So when I react with Br2, I expect the Br to connect either here or here, which is the same either way due to symmetry. And then I just need to use the dilute sulfuric acid conditions to remove that sulfonate group and replace it with a hydrogen to get to that product. So you want to at least be aware of how the sulfonate group can be used as a blocking agent, and based on its resonance, why it's a meta director and deactivator, and how that affects the process. All right, so that gives us a lot of options now. We know we could take benzene and we can install a variety of groups there. We know if there's already something on the benzene, if we install another group, where it will end up with respect to the initial group. You want to be aware of some of the things we talked about previously, before spring break, and also prior to that, for how certain groups outside the ring can be reacted. So you can reduce a nitro to an amine. You can convert a methyl into CBr3 using NBS, right? This is a reaction. Oh, that's not correct. Actually, maybe it is correct. But it's also from chapter 11. I think that actually is correct. 18.6, but also chapter 11. The free radical chapter, right? So if we're using NBS, that produces bromine radicals, which would abstract to hydrogen to produce a resonance stabilized carbon radical, and then that would pick up a bromine. So you need excess to do that 3 times. We also talked about how you can oxidize any alkyl group as long as there's at least one hydrogen attached to this carbon. Using these very strong oxidation conditions, any other carbons connected there would be disconnected. All the hydrogens would be removed by this reagent, and you'd fully oxidize that to a carboxylic acid. So we want to practice enough to familiarize yourself with those reactions so you can use them as necessary on an exam in a synthesis or reaction prediction type problem. All right, so let's look at a couple more examples. So we've got 3-nitro, bromo, benzene. We want to make that. All right, so let's take a look at what that would look like. So we've got bromobenzene is the name of my structure. Bromine here. 3-nitro means a nitro group on carbon 3. So how do I install a nitro group meta to a bromo? Well, I've got 2 options I could take, if I'm starting from benzene at least. I could put the bromine on and then install the nitro, or I could put the nitro on and then install the bromine. In this case, I don't want to put the bromine on. I have to know from experience and be able to rationalize that through the mechanism that the bromine, because of its lone pairs that can donate into the ring, is an orthopara director. If I put the bromine on first, the nitro is only going to end up ortho and para rather than meta, which is where I'm trying to position it. So that means I've got to start with the nitro group first. So I would do HNO3 and H2SO4. Those would produce the nitronium ion. The ring would connect to the nitronium ion. Then after re-aromatizing, it would install the nitro group. Now the nitro group is a meta director. So the next reaction I do is going to position the bromine at one of those 2 spots, which is the same due to symmetry, doesn't matter which. So I'm good to go there. So I'd add Br2. In this case, it's also a deactivator, the nitro group that is. So I would need definitely some kind of catalyst, like FeBr3 or AlBr3 to help facilitate that reaction kinetically. And that should give me the product. Let's take a look at how to make 3-chloroaniline. So aniline implies you have an NH2 group at carbon 1. So if I count to 3, put a chloro on carbon 3. This is the compound I'm trying to make. Well, this is a little bit more challenging because both of these groups are ortho-para directors. If I start with the amine, it would direct ortho and para to it, not meta. And if I start with the chlorine, because the chlorine as well as the nitrogen can shift electrons in through resonance, I would also direct the next group to come ortho or para to it, not meta. So I've got these two groups positioned meta with respect to one another. So what I need to do here is start with a group that's a meta director to help install the other group meta to it, and then do a functional group transformation that will convert it into the final structure. So what we saw over here is going to allow us to do that. This reaction right here is the key to solving this. The nitro group's a meta director. It can be used to install something meta, and then these conditions can be used to convert it into an amine, and that's also shown over here. Right, so this is a common theme. If you want to start with a meta director, connect something to a meta position, then you can reduce it to something that would have been an ortho-para director. And so there's a couple different examples of those types of things. So here, though, what I would start with, if I were starting with benzene, is I would put the nitro group on first. Now that that's a meta director, it's also a deactivator, so I definitely need a catalyst. I would use Cl2 and AlCl3 as my catalyst, and that should then do the chlorination, at least on paper, at a position that's meta to the chloro. And then to get the final product, I can use iron or zinc with HCl. Here they're just using zinc. And that should reduce the nitro to the amine, right? So again, then oxygens would be picking up protons to make water leaving group. The zinc would bring in electrons to push them out, and then those electrons would pick up more protons, and you'd end up with an amine group there. So I would look back to this slide as necessary, because you're going to end up, if you practice enough, in situations where maybe you need to start with an ortho-para director to install something, but then you have to convert that ortho-para director into a meta director, so you want to be aware of how these reactions work to do that. A few limitations on the EAS reaction that are going to be relevant if you're solving synthesis problems. One is, you can't do a nitration of an amine. And the main reason for that is because the conditions that you need to add a nitro group, which are HNO3 and H2SO4, are very strong acids. So any group that's reactive toward a strong acid is going to react with that very readily under these conditions. So this nitrogen would end up picking up a proton from here or from here, and it would end up producing this, which is no longer an ortho-para director, and it's a really serious deactivator because it withdraws electrons so strongly due to being positively charged. So if I try to react this, it probably wouldn't even react because it would be pulling electrons away so much. The electron density in the ring wouldn't be rich enough for it to come out here and bring in the NO2, and even if it did, it would do so meta to avoid a positive forming on the carbon right next to the nitrogen, which causes a huge amount of repulsion and makes it very unstable. So that's a limitation. It's a reaction you just can't do, even though you might otherwise think it would work. One other limitation you want to be aware of, this is something we talked about before, you can't really do the Friedel-Crafts alkylation if you have any deactivating group. Because as we said, those groups pull electrons out of the ring, creating a lot of partial positive in the ring. And so the ring is just a much weaker nucleophile than it would otherwise be. It's not going to be very good at coming into a partial positive and pushing out a leaving group when it's already partial positive itself. So that's another limitation. Right, so this situation where the activation energy would be prohibitively high for these reactions to work in any practical way. All right, what if I wanted to synthesize this structure? Well, how do I get a carboxylic acid group on a ring? The only reaction we've seen recently that allows you to do that is this one here. So if I start with a methyl group or other R group that has at least one hydrogen bonded to the carbon directly attached to the ring, I can use potassium permanganate to convert that into a carboxylic acid. So the idea here would be working backwards, retrosynthetically. If I start with this xylene, orthoxylene structure, or 1,2-dimethylbenzene, that could be converted into the product using potassium permanganate and some heat, followed by H3O+, which is just necessary to get those protons on there at the end. So how would I make this structure? Maybe I want to make that from benzene. Well, benzene isn't deactivated, so I could use methyl chloride with AlCl2, and I just use a little excess. One of those reactions should install one methyl group. Once that's installed, it's electron donating, so it's activating the positions that are ortho and para to it, and since it's not very sterically hindering, the ortho positions aren't blocked, and there's two of them compared to the one para, so it's twice as chance of that occurring statistically. But there is some sterics there, so that chance is diminished a little bit, but still more of a chance it'll connect ortho than para. And so if I do that twice, the second methyl group should end up ortho to the first one, and then the oxidation can produce the dicarboxylic acid group. All right, what about this one? So this is even more challenging here. I've got three groups to connect to this benzene ring. And so I have to think about what order do I want to connect them in. What's going to help me with that is to figure out which groups I need to install first so that they'll direct the subsequent groups to the correct position. So one thing I would want to start by doing here is just to recognize for each group, is it an ortho-para director or is that group a meta director? So since the bromine is an ortho-para director and the other groups are ortho or para to it, I probably want to put that on first. But sometimes it's also helpful to work backwards. Which group should I put on last? To answer that question, I can imagine, well, what if these two groups were here? Would they direct the last group into the correct position? Yeah, because the bromine would direct this ortho to it, or para to it, and the nitro group would direct it meta. So if I had the bromine already here, and the nitro already here, would that work? The bromine would direct the next group to come in ortho or para to it, and the nitro would direct the next group to come in the same positions, because those positions happen to also be meta to the nitro group. But the problem is the bromine isn't very sterically hindering, so there's no way to really control which of these two positions this last group goes to. So I actually probably don't want to add that one last, because if I add that one last, I can't control which side it really goes to. So what if I added the nitro group last? If I start with the ring already having the bromine and this acyl group, would the nitro group go to the right spot? Well, the bromine is going to direct it ortho to it because the para position is already occupied. And this is also a meta director, so it's going to direct the last group to go meta to it and those two positions are equivalent, symmetrically equivalent. So this is the kind of thing we're looking for. Working backwards, we recognize we want to put the nitro group on last, because if we put it on last and these two other groups are already here, they'll both direct the nitro group to the same desired position on the ring. And once I know which group I want to put on last, then I definitely know I want to put the bromine on first, because it's an orthopara director. I'll direct this group over here, para to it, and this group maybe second. I wouldn't want to start with this because it's a meta director, and it would direct the bromine meta to it rather than para. Right? So that is what I would do synthetically. Start with the aromatic ring, add the bromo, recognizing that the bromo is an orthopara director. When the bromobenzene reacts with this, it would also give me the product where this acyl group ends up ortho. So because it's a fairly large group, it might create some sterics there. Maybe that would be a minor product, even though the bromine is only a single atom. It's not very big as a group. But this would definitely be a mixture of those two, and I'd have to separate out the desired one. Then I could add the nitro group using these conditions, and the nitro should end up orthopara to the bromine and meta to the other group. So that's also, again, the type of thing where you want to practice that a fair amount so you get used to seeing where these groups are going to direct the next group to attach. And so now finally we can talk about the last quiz question for today. So here I've got this benzene ring, and basically the idea is I want to install this butyl group, and I want to install this group here. So which do I want to install first? Well, they're both electron donating at the moment, so I really could install either group first. But I also I have to think about how I'm going to get this here, because this is something we haven't really talked about. So working backwards, what reaction can I use to make this OH group here? And what would this group have looked like prior to that reaction? Well, let's maybe work forward. Right? So maybe I want to think about two different routes. If I want to install maybe this bottom group first, how would I get that on there? I can't really use Friedel-Crafts directly, because we know using Friedel-Crafts to connect a carbon group to a ring, that usually works as an alkylation. If I have an R group, I can connect that to the ring. Depending on the R group, it may or may not work. I can do an acylation, where I've got a CO double bond there, and that would give the CO double bond connected in there. And so knowing that that reaction is possible, now I'm thinking of how this will work. Because I know CO double bond can be reduced to an OH group using lithium aluminum hydride or sodium borohydride. Those reagents will use a hydride to attack the carbonyl, and that will convert that into an alcohol. So that's basically what I need to do. So do I want to do that first or after? Doesn't really matter, actually, the order, since, as we said, they're both orthopara directing groups. But I also know this butyl group's not easy to install, right? So if you're thinking that you want to install the butyl group by using chlorobutane and AlCl3 to get that butyl group to attach, that's not going to work. All right, last time we said if the leaving group's on a primary carbon, it can't just leave and then have the ring attack. And the ring can't attack and push it out because there isn't enough partial positive or really enough negative here to make the attraction. They're too stable to begin with. The transition state would be too high compared to the stability of the reactants for the reaction to happen very often. So what we said would happen is once this chlorine connects to the aluminum, it'd be likely for a hydride to shift over and push it out. But then my positive would be on the secondary carbon, and the ring would attack there, and I wouldn't get the primary carbon connected to the ring. And so that's why that won't work. So if you want to install a primary carbon to a benzene ring, typically what you need to do is the acylation. So in the first step here, if I want to install the butyl group first, I need a 4-carbon chain there, and I need a CO double bond. Right? That way, when the chlorine leaves and goes to the aluminum, the acylium ion will be stabilized by resonance, and then the ring can attack that. And so that will give initially a CO double bond at that site on my 4-carbon chain. Now that's a meta director. So I don't want to install a second group yet. If I try to install a second group, it'll end up either here or here, rather than in the para position where I want it. So the next set of conditions, I would probably use the zinc and HCl to reduce the CO double bond to the alkane. And now I've got the butyl group where I want it. And it's pretty sterically hindered, so it's probably blocking the ortho positions, even though it's an ortho para director. Those will be blocked by sterics fairly well. And so I expect the new group to come into the para position. And the new group I want to add is this. So what's that group going to be? It's going to be an aromatic ring, this ring here, bonded to a carbon, this carbon here, and it's going to have a CO double bond with the chlorine. So after step 3, this butyl group should direct this carbon, right? The chlorine's going to leave and go to the aluminum, creating another acylium ion, stabilized by resonance. But then the ring, this ring, is going to attack that from the para position due to sterics blocking the ortho position and due to this being an orthopara director through induction and hyperconjugation. So that will allow this structure to form. And so then to get to the final product, I need lithium aluminum hydride followed by water and or potentially H3O plus. Those would have to occur in 2 separate steps. I could also use sodium borohydride and water here, but the lithium aluminum hydride is a stronger reducing agent. There's no other site where it would react, so it'd be better to go with the stronger, more reliable reagent to deliver a hydride there, push electrons up, and then the H3O plus or water would protonate that and give you the alcohol. Any questions about that? All right, well, that's only a few bullet points, but there's a lot of variety in those, so you want to practice as much as you can. And prepare for next time. Next time we're going to be finishing out chapter 19 and getting into chapter 20, which is more about CO double bonds. So there's a lot of good videos there to help you with that reading and help you answer the quiz questions for Wednesday before we go over that content. So feel free to reach out anytime with questions, including right now if you have any.